The Earth. Is it really just a big ball floating in space? Spinning on its axis at 1,000 miles per hour? Hurtling around the sun at 67,000 miles per hour? Whizzing through the Milky Way at a milk-curdling speed of over 500,000 miles per hour? And warp driving through the heaven at over 500 million miles per hour? And what about the sun? Is it really 93 million miles away and close to 1,000,000 miles in diameter, with a circumference of nearly 3 million miles? And it's constantly illuminating half of our entire Earth's surface with the rotation of the Earth, creating our 24-hour days, our night and days? Maybe the Earth is flat after all. And maybe it's completely still, just like we experience. And maybe the sun isn't big, but is very small and very close, and not illuminating the Earth from 93 million miles, but is illuminating locally. And maybe everything, the sun, moon, and stars, are not far away, but are circling overhead relatively close. In this video, we're going to explore the latter option, and at the end, we're going to reveal startling evidence through the use of time-lapse photography that the sun cannot possibly be 93 million miles away, but is in fact very close and is illuminating locally as it traverses our flat Earth. Oh man, and watch how this sun comes at you. Boom. I mean, come on. And that's all perspective. That's if you look at jet trails, Google Images, you'll see them. They start out low at the horizon, they come up overhead. Look at that thing. They come up overhead and then they go down to the horizon. Perfectly explains what the sun would do. Here it is going overhead. I love time lapse. Look at this. You can't go out and look at the sun. You can't see this stuff, except that it's on, time lapse like this. It's incredible. Now watch this thing. It's sweeping. The sun over flat Earth is doing a big circle, right? Look at this thing. See it sweeping to the right. It's like a lefty bowler. Just toss that down the alley, and there it goes, hooking into the pocket. Again, you can see how the clouds angle down to the horizon. Show it there. That's exactly how the sun would do. Okay, back to the Copernican principle, and this is what they tell us. The sun is 93 million miles away. Now, I'm going to show you evidence through sunsets that shows the sun light following the sun over the horizon, and it shrinks as it goes over. Now, there's no way it would do that if the sun is 93 million miles away. Okay, first I'm going to show you some footage from the ISS. Okay, now watch this animation. Watch this sunset. Now this is exactly, if they came to me and said, do an animation, this is how I would do it if the sun were 93 million miles away. Just like that. Have the whole horizon light up and then fade evenly across the whole horizon. But that's not what we see. Okay, wow, look at that. Look how the light lifts off the ground like a big wedge, or like lifting up a sheet of paper. That's incredible footage. Definitely the light's following the sun, right? Okay, next I'm going to show you how a sun that is circling over the Earth, that creates the horizontal aspect of the sun. If you combine that with perspective, which creates the up and down of the sun, the rising and the setting, you get the 23.5 degree tilt that they talk about. It's nothing but perspective and the circling sun. Here's another sun sweeping out a big circle. here's a phenomenon that you might be wondering, how in the heck do you explain this on a flat Earth? Well, this footage is taken from Alaska during the summer, and the sun does look like it's going up and down. And what the problem is, the reason it's doing that is that this town in Alaska is not in the center of the sun's circular circuit. In other words, the sun is making a big circle, and the town is not in the center of that circle. So the sun will appear to be closer and further from the viewer with the camera. So that will cause it to go higher and lower, and also maybe even bigger and smaller. The high altitude airplane. Remember, this is from a high altitude balloon, so that airplane is probably at cruising altitude. Notice how it looks like it's going up from the horizon. That's exactly how the sun will rise, because that plane is staying parallel to the ground. And now watch, it'll go down to the other horizon. All right, again, perspective, that's how the sun will set. And forget the big ball, that's just due to a GoPro camera. But see how the sun, that's the point of this. And then also, look at the size of the sun, man. Look at that thing. I mean, there's something to it to say that we're higher up our view, and the sun looks bigger, and it looks like it's not as high in the sky as it does when we're on the ground. Something to that. Let's explore this notion a bit further, that the sun looks bigger when filmed from higher up. The next 3 slides, I'm going to do a comparison, a side-by-side. The one on the left, the camera's above the clouds. The camera on the right is ground level. Okay, here's a little illustrator or a little cartoon from a website called timeanddate.com. It's really funny that they would have a perfect illustration of a sun rising and setting on a flat Earth due to perspective. You'll notice that that it rises from below the horizon and sets below the horizon. Now you might be saying, well, how is that possible? I can see now you're saying that it rises and lowers due to perspective, but how does it disappear below the horizon? Well, I got a theory about that. Because of the fact that all parallel lines and planes converge at your eye level horizon, this is according to the perspective, I'm not making this up. If in fact, and they do, they converge at your eye level horizon visually, then it makes sense that after that point they diverge, meaning they then separate. So the sun would continue on a downward track. As you can see from my illustration here, the lines would go to your horizon, and then afterwards they would spread out and separate, kind of like a starburst, and the starburst being at your horizon, at your focal point. Anyway, without further ado, we're going to start talking about, and I'm going to start showing you the time lapse of the sunsets that I'm talking about that clearly show the sun is close and illuminating locally. Here we go. Here's one right here. I'm going to save the best for last, of course. You can see the light fading. Again, they didn't hold it quite as long as I would have liked them to hold it. Here we have one going over, and you can see the light trailing the sun. Okay, these next three slides, the sun is almost set already behind the horizon, but watch as the sunlight shrinks and follows the sun. It's definitely a locally illuminating sun, not far away, not very big, and definitely not 93 million miles away. Okay, remember this video from the beginning of the video? I showed you this one and how it's circling over the earth, and watch it sweep to the right like a bowler bowling it in there for a strike. Okay, now I want you to pay attention to the way the light follows the sun. The sunlight's going to shrink, right, as it follows the locally illuminating sun. Now watch this. See it shrinking, following the sun? You do not get that if the sun is 93 million miles away. The entire horizon should light up. This is proof right there that the sun is close, illuminating locally, and traversing over a flat earth, period. So these time-lapse sunsets are definitely the nail in the coffin for heliocentrism, but this particular one here, shot from above the clouds from this observatory, is the final nail in the coffin. Look at how the sun just shrinks and the light shrinks to nothing. That cannot happen, as I showed you in the when the sun illuminates the entire Earth, which it does from 93 million miles away. It has to. You don't get this isolated look at the sunlight trailing the sun. That's only possible with a small sun, close, not very high, illuminating locally. I mean, if this isn't proof to you, then you gotta take the blinders off. Okay, and finally I want to show you some examples of local illumination, or a city in the background. This is from Grand Canyon National Park. That you can see Las Vegas is one of them. You can see the stars going down, so you know that's not the sun. That's the glow of Las Vegas, it says. You can see that's local illumination. I'm just making an example showing you here's Tuba City and a little bit of Flagstaff. Now, in this one here, you see two lights. Obviously, we don't have two suns, but these are two cities lit up, and it's just to show it looks just like the sun going over the horizon. That's the point of me showing that. That's local illumination at work. The sun is not 93 million miles away, because if it was, the entire horizon would light up, or actually would fade evenly, and the entire horizon would fade at the same time. Not what we see here, which is the small sun cruising over the earth and the light is following it. Case closed.
The earth is flat, living in illusion. The earth is flat. We take some illusion. The earth is flat, living in illusion. So people don't know what to do. The earth is flat, living in illusion. The earth is flat, it's staging illusion. The earth is flat, living in illusion.
In the first video, perspective taught us that all parallel lines and planes angle to our eye position. But will those parallel lines and planes angle up to our eye level if we go high up, like atop a tall building, or from an airplane, or from over 100,000 feet in a weather balloon? Will the horizon still be eye level? That's what we'll be looking at in this video, but let's review. All of the lines converge at a center point on the horizon called the vanishing point. Parallel lines above it angle down, the lines below angle up, the sides angle in. The vanishing point is the intersection of the horizontal and vertical axis of our eye position. It's parallel all the way out, parallel with the ground. That's why I say you can't look down at the horizon, because the horizon angles up to your eye level. The two, your eye level and the ground plane, are parallel all the way to the horizon. But it's the bottom ground plane that angles up to your eye level. Also, the vanishing lines tell us where the camera was when the photo was taken. You can't look down at the horizon because the horizon is at the height of our eye plane. It's not where your eyes are looking that determines the horizon, but where your eyes are located. It's the height of your eyes relative to the ground. Our eyes work like this. Our eyes shape what we see into a cone. All parallel lines and planes angle to the plane of our eye level. Here you can see parallel lines made up of bricks on the walls. The wall on the left, though, is headed out towards the horizon, and all the lines angle toward the eye level of the observer. The bottom ones angle up and the top ones angle down. The horizon would not be eye level, but visually ground level if the bricks angled down to the floor like this. That the parallel lines do not angle or converge towards the ground, nor do they angle towards the ceiling, nor to the left or right. They angle to the eye level of the observer. This image is a product of our eyes. These are horizontal parallel lines, yet we see them not as parallel, but on an angle towards a point in the distance. Now, of course, we know that they are parallel, but they visually are not. These lines are visually parallel. Our eyes visually intersect the parallel lines at the horizon. And the horizon is always a straight line because it's always eye level. And we know it's always eye level because it's always a straight line. Straight line, straight horizon. Sitting in a boat in the middle of the ocean, you will be encompassed by a 360-degree horizon that's a straight line and it's eye level. Here's an illustration. Try this out for yourself. You'll need a flat circle like a hula hoop. The only way to make that 360-degree circle appear as a straight line is to position it so that it is perfectly on plane and level with your eyes. Go ahead and give it a try. Perspective demands straight level parallel lines and planes. A progressively downward sloping Earth is not a straight parallel line, so I don't know that it would make it to the eye level horizon. And as we know, all horizons are eye level because they're all straight lines. So I really have my doubts as to whether or not the Earth is a globe. Globe or a ball, at some point it would be below eye level because the ground is sloping away. It's sloping away right from the observer. Wherever you are, you're on top of the world. You are the high point on a ball. So the ground slopes down away from you. But there is the law of perspective. But again, like I said in the last slide, perspective works with straight, level, parallel lines. And a downward sloping Earth is not a parallel or a straight line. So, some would say, well, but it's such a gradual slope. I've seen videos all over YouTube where they're looking out at a water horizon that doesn't look very far, a few miles out, and they're saying it's obscuring a building behind it. Well, that's quite a bit of curvature, wouldn't you say? It could obscure a 10-foot, 12-foot building behind a wall of water. So I would think at some point you would have to look down at the horizon and it would look like a curve. The horizon line would be curved, but we haven't witnessed that. We don't see that. I go in this video, I'll go all the way up to over 100,000 feet and it's a straight line. So here I've overlaid a hallway over the water so that you could see perspective at work. It works in the hallway the same as it works on the water. It's just that over the water there is no walls and there's no ceiling. But the principle is the same. And then I take this hallway, I fill it with water and spread it out so that it equals the horizon up to the horizon line, and then remove the top half and you have the same lower plane horizon, as I call it. Next, I'll demonstrate perspective with a couple of pictures inside long corridors. If you're thinking the horizon is produced by the curvature of the Earth, you'll see that the horizon and vanishing point is formed in a relatively short distance. You cannot attribute the horizon and vanishing point that is formed in these pictures to any kind of curvature. Okay, and here's what we could expect to see if the Earth were concave. The horizon would be above eye level and it would be curving upward. We do not observe a concave or convex horizon. The horizon we observe is always a straight line, and as we've learned in this presentation, a straight horizon line means the horizon is eye level. This one we observe, the others we do not. Let's go up higher and see if perspective still holds true. A camera height of 1,368 feet, the horizon line, eye level, and it's dead straight. This is atop the old World Trade Center. How do we know the horizon is eye level? In order for our 360-degree circular horizon to appear as a level straight line, it must be eye level. Try holding a hula hoop up around eye level and position it until it becomes a straight line. Here we have all parallel lines and planes, yet they look as though they converge, and they converge at a point on the horizon called the vanishing point. Everybody sees their own horizon depending on where they are and how high up they are, because the horizon is a product of our eyes. Again, it's our eye height that dictates the height of the horizon. Let's add some brick walls to the sides of the World Trade Center so we can see those parallel lines. Laws of perspective have not changed just because we're higher up off the ground. You now know that the horizon is eye level and that it's a product of your eyes. The converging horizontal parallel lines to your eye level proves it. If you had a big window at the end of this hall, the horizon would be at your eye level, and the lines on the walls would verify that. Well, that completes our review of perspective. Let's go higher up and see if the horizon still remains a straight line and still eye level. Straight line, eye level. How about atop Mount Everest? Again, that's a straight line. Remember our hula hoop, it's got to be eye level. Again, Mount Everest, straight line, eye level. And one more time, straight line, eye level. How about from an airplane window 30 or so thousand feet up? Straight line, eye level. Straight line, eye level. Never changes. Just wanted to throw a little more in here about the about perspective. And this, with this photograph, you can see I have the XY axis, that's the horizontal and the vertical axis, and then you have the Z axis, which is the longitudinal axis. That's from your eyes to the vanishing point. Now, I pointed out and I marked it with a green line that airplane streaking across the sky. So that's probably, let's say that's 38,000 feet, and the airplane here that you can see the wing of is 30,000 feet. So I'm going to assume that airplane streaking across the sky is at its cruising altitude and it's parallel to the ground. Well, one thing you'll notice that, and this is what perspective demands that straight, level, parallel, that's the key, parallel lines and planes will angle to the horizon and the vanishing point. Okay, that's all the red lines. Those are all going to the vanishing point on the horizon. That's if they're level, if they're parallel, straight lines and planes. Okay, now that green line represents the flight of that plane. Now you can see that it's probably parallel to the ground. It's parallel to the x-axis. Therefore, it'll bring it down to the horizon, and that's where it'll disappear. Now, why isn't it headed for the vanishing point? Well, the reason is because it's not parallel to the z-axis or the longitudinal axis. If it were parallel with that, it would follow one of the red lines that take you right to the vanishing point. The exponentially downward curving Earth could not make it to the eye level horizon. And again, how do we know that it's eye level? A lot of people get irritated with that. How do you know it's eye level? Because it's a straight line, as you've already seen with my hula hoop example. It has to be. So that's strong evidence that the Earth is a plane and not a spherical ball. So, because no matter what altitude, and I'll show you, I'm coming up with even higher altitudes coming up in this video from weather balloons. So anyway, we'll save that for another video, but let's continue. So the horizon that we see is always a straight line, which means it's always eye level. In order to see a curved horizon, it would have to be below or above eye level, but we don't see that. The only time we see that is when people use fisheye lenses to film. Otherwise, it's a dead straight line. Well, let's not stop at 30 to 38,000 feet. Let's go all the way up to 100 or 120,000 feet. These are a few stills from amateur weather balloon footage. Apparently no fisheye lens. And you can see it's a flat, straight horizon. And if you've been paying attention, you know what that straight line means. That's right, you guessed it. Eye level and no curvature. And for anyone that claims that they've looked out their airplane window and saw curvature, which means that the horizon would have to be below eye level, remember the footage from the amateur balloon. That's 100,000 feet. The airplane's about 38,000 feet. If you can't see curvature from 100,000 feet or 120,000 feet, you certainly couldn't see curvature at 38,000 feet. I'm just saying. And, by the way, in case you didn't know, as cool as this picture is, it's not reality. The next 3 slides are from a high-altitude balloon video that used a fisheye lens.